Okay, so let's continue the course and finishing the controller design. In the previous class, guys, we had this example of, if you remember at the end, this example of here was X was unit step. Oh, thank you. Okay, there you see it. Yes. So in the next, sorry, in the last class, we had this example with the unit step as input, and we designed the PD controller KP plus KDS in mathematically and in MATLAB, and the system was second order system was like this: S, if I'm not wrong, because I'm teaching from my mind, S plus 1. Am I right? Yes. So, and we saw that the system originally was system had a pair of complex conjugate poles. Okay, this system, but we added the controller C, and this is G, open transfer function of the system, because your boss or me, I ask you, you know what? So when you see a complex conjugate poles, as you saw, your system was underdamped system like this. But your boss said, you know what? This is a robotic system. This is whatever system. This is like, I don't know, the shake absorber for the building. I want to have the critically damped system. And your boss said, I want to have the critically damped. So desirable poles, if I remember, was -1. So we ended up designing the controller KP and KD, and we changed it, if you remember, to a critically damped system. Yes, also in MATLAB coding. So the question is that I have a question from you guys. Why I didn't add integrator, I controller. I only stick to the PD controller to make this happen, to make it from the underdamped to the critically damped system. Look at here, guys. The answer is here. Exactly. Excellent. So, because system by itself in the open loop always, and this is a lesson for you after your graduation, if you see a system after linearization in the feed forward path, this is feed forward path, that's right, has integrator by itself, so don't do that. S plus 1, that's right. So the system, as your friend said, already have integrator here, 1 over S. And that's why when we design controller, you have no steady state error signal. Steady state error is 0 here. Right, everyone? Understand? Yes? So your system already has integrator or controller. See what I'm saying? This is a very important point. Okay, guys? Now? Yes. Okay. So, what I did is, based on mathematics, based on the behavior that you want to have, I designed 2 types of controller for 2 different systems. But there are 2 classical methods by Nichols-Ziegler or Ziegler-Nichols. Ziegler-Nichols PID controller design. But before going that, there are 2 methods, 1 and 2. I'm going to teach and finish the controller design. The next class, I'm going to hint Ruth Lucas in this class, mainly on the MATLAB and the concept of that. Okay. Okay, let's do that. Remember, I told you that the PID controller is Kp proportional, KdS derivative, plus KIS. Now, if I factor out from Kp, it can be 1 plus Kd over Kp in S, plus Ki over Kp over S. Now I can define new parameters based on the standards of Ziegler-Nichols. So your PID we are writing like this: 1 plus TDS. TDS is Kd over Kp, plus 1 over TIS. This is for derivative, this is for integrator. TIS. See? Here we are. So obviously TD is KD over KP. You don't need to calculate that, because eventually you see that I'm gonna give you a table, and the TI is KP over KI. Okay. Let's write it down because I have to delete all of those. So based on the Ziegler-Nichols, we're gonna define PID like this. Okay. Can I delete that? Yes. Everybody? So I'm putting the controller here. Kp 1 plus TDS plus 1 over TIS. This goes to, this is control command, U, remember again. This goes to the plant. Plant can be your car, can be a robot, can be satellite, whatever. Have you seen the super heavy shuttle by the Elon Musk? So you can put plant here super heavy, exactly because what their scientists doing, they are designing controller. That's it. This is the super heavy shuttle. So they're gonna design the controller. I'm not saying that they are designing PID controller. Maybe not. Maybe they are going to nonlinear, which is graduate school topic, okay? And then it's being fed back to trajectory that the shuttle wanna go. Okay. So having this, the first method of, can I go to next page? The first method says, if you apply, oh, that is dancing line. If you apply step unit as the input to the system, desirable input, if I apply this step input, here we go. So this is valid for any system, third order system, fourth order system, fifth order system, 10th order system, 20th order system, whatever. And your system to the response profile is S-shaped. This is, we name it S-shaped because it looks like the S, that's right. This part is like as S, S-shaped, S-shaped. If response to unit step is S-shaped, Okay, guys, in the inflection point, what you're gonna do, you're gonna tangent the line here in the inflection point here. Okay, you're gonna do that. Then let me cross this line. Okay. Then you're gonna name this until 0. This is time 0, right? You're gonna name this as L. L means delayed term, because it takes delay to raise up, right? Then you're gonna name this as T here. Rise time. Remember rise time that I was teaching you for the first and second order systems? And the final value that it caused is K. Here is K. Okay. Guys, look at here. Please look at very deeply here. Okay. Is this familiar to you? Have you seen this before in this class? This part. Have you seen this? This is the response to the first order system, remember? So on the other hand, you can say your output over input can be modeled as delayed. Delay in S domain is E minus what? LS. This is delayed. This is time. LS. K value. And the first order system. So it's going to be TS plus 1. If your response, which is third order, fourth order, 20 order, to the input step is like a delayed S-shaped, you can model it as this. Remember, if the Laplace of, for refreshing your mind, f of t is f of s, when I say delay, you're having a notice, I taught you. Laplace of t minus t naught, which was delay, was e minus s t naught f of s. Remember? I taught you this. So when I say delay, means this s. So, but again, the condition is that your response is S-shaped. So, having that, Ziegler-Nichols says, I have to go to next page if you are done. Can I go? Okay. Yeah, no? Okay. Says, after finding those L, T, and K, you can use this table and find your KP, TI, and TD of your PID or P or PI controller. This, you're gonna have this, and this. This is type of controller. P controller, to stabilize the system or tune the natural frequency of the system, saying PI controller. When I say PI controller, it means stabilizing the system, tuning the transient response, and removing the steady state error signal. Or PID controller. Okay. Ziegler-Nichols says your KP, TI, and TD that we defined here, PID controller based on these new parameters. If you want a PID controller, gonna be T over L. From the graph, you have to T over L. Because it's P controller, so your Ti is infinity. Why? Because 1 over infinity is 0. This goes away. And TD also is 0. So you have only P controller. Clear, everybody? Yes? Yes? Good. If you want to design PI controller based on that, it's gonna be, let me change the color, 0.9 T over L I controller, L over 0.3, and the TD is 0 because it's PI controller. If you want to have full PID controller, it's gonna be 1.2 T over L, 2L, and 0.5 L. What? And only for this only valid when the response to the unit step is the S-shaped only. Okay? And that's a good question because Nicole Ziegler, they are doing great, but it's very limited approach because most of the system, they don't behave the S-shaped. See what I'm saying? Okay. But if you have such a system that is like as S-shape, I'm going to do that in MATLAB today. You can use this table for designing controller. Okay? Understand? Okay. So now let us assume that I want to have the PID controller. So this is again, this is G of C, that's right. This is plant. This is open loop of the controller. So by saying that open loop controller is PID, KP based on whatever we did, plus TDS plus 1 over TIS. For example, I want to have the PID controller. So it says 1 over 1.2 T over L, 1 plus TD is 0.5 L, plus 1 over 2 LS. If you multiply, oh, I forgot here S. If you multiply this and do some operation, you get that based on the Ziegler-Nichols, if you want to implement the PID controller, it's going to be like this. S plus 1 over L square divided by S. Okay. Understand? So it's enough that you plot in MATLAB, get the T and L, put here, it's going to give you your controller. And you see your controller has how many zeros and poles? Please give me the answer. Just now you have to be expert of that. How many poles does your controller has? What's the pole of the controller? Pole of the controller. 1. It is at origin. Here we go. How many zeros it has? Yes. Repeated real zeros. 1 minus over L. So you see that even controller, as we saw previously, imaginary and the real, has a pole at the origin and 2 zeros, say here, over each other, 1 minus L. here by the Ziegler and Nichols. Okay. Now let me go, because I have to play a little bit in MATLAB to find such a function and then design it. So that's why I taught you guys in the last 2 or 3 classes that use mathematics of natural frequency and zeta to find Kp and Kd, remember? Because that's very general and solid. You can do that based on the sense of engineering and the calculations. When it comes to Ziegler-Nichols, you have to have such a system that is S-shaped. Okay, but let me do that. Okay, so it's MATLAB. Okay, let me see. Num is a third order system. You know what? A equals to 1 and 1. Bear with me, I will teach you, okay? 1 and 6, 1 and 10. T is convolution of A and B. And E is convolution of D and C. Okay, so guys, because I have to refresh my mind, if you have 2 vectors, okay, because I'm writing here because I'm going to develop with you. You have suppose, let me go back to this. I have to teach you these tricks in MATLAB. Okay. Suppose that your y over x is this 1 over s plus 1 in s plus 6 in s plus 10. What's the order of the system, for God's sake? What's the order of the system? Yes, but you don't have to do by hands, because this is a vector A. Vector A is 1, 1. Vector B is 1, 6. Vector C is 1 and 10. So in MATLAB there is a command. It says the product of this, I'm saying, is D conv A and B. When you got that, your E gonna be conv. I forgot that you can do 3 together, but I'm gonna try. C and D. So it gives you the third order system coefficients. These. See what I'm saying? So let me do that. So A is 1 and 1. B is, I'm going to share with you, 1 and 6. C is 1 and 10. I'm not sure that this is going to give me all together. I don't think so, but I'm going to try. Because I did a while ago, 10 years ago. So I'm going to say delayed PID. Okay, if I run it properly, yeah, because it says, okay, 2 vectors, and the coefficient gonna be conv and C and D. So say it's gonna be S cube, S square, S1, S naught. So this is your what? Your system. So num gonna be 0, 0, 0, 1, and then because I have to examine the numbers to find that 1, it's gonna be our coefficients, right? Coefficients. There we go. Now if I plot this figure 1 step, no, and then hopefully this works because I never did this. Yeah, kind of. Do you see that? It's kind of S-shaped. Kind of. So let me change the number and I put this also 10. Yeah, much better. So let me increase the numbers to 20. Bear with me. I'm gonna tell you how I find those. Oh, that's too much. 15. 10 is much better. 12. 10. Okay. So guys, do you know why I selected this? Here, let me fix it. 10 and 10. Do you think it's just random that I selected? What do you think? Why I selected 10 and 10? Give me the answer. Give me the answer. What do you mean? You are very close, but I want to know that you know the answer. What do you mean? Huh? No, no. Guys, I told you in the Ziegler-Nichols, this is the unit step, that's right. So your y gonna be, at the end of the day, s plus 1, because this is unit step, s plus 10, s plus 10. Yes or no? Yes. And you know that how we were finding y? We were decomposing to a over s plus b over s plus 1, remember? Because this is squared, it's gonna be c s plus 10 plus d s plus 10 square. Do you remember that we were doing this? Huh? Now I want to go to find y. Laplace inverse. The output of the system gonna be, look at here guys, a unit step plus b, if you remember the first order system, e minus t, this one comes here, plus c e minus 10t. That's right. See what I'm saying? Yes? Huh? and D whatever. So you see that which of them vanishes fast between these? Yeah, so these are vanish so fast. You physically you say my system is a first order system. See what I'm saying? Yes? Because those poles, and remember that I was teaching you dominant poles, that is 5 times of the other poles, they're gonna vanish fast. Those poles are very large, they're gonna vanish very fast in time. So your system is S plus 1. See what I'm saying? So having that in the hand, hopefully it works, okay? Because I didn't try it before. So I'm gonna go here, for God's sake, and say insert a line. And my line gonna be this. Because I told you in the inflection point of this system, we have to we have to find the inflection point of the system. Here it is, This is inflection point. Yes, we are doing that. Okay, I plotted that. So I'm gonna find what the L say here. Okay, this is not exactly what I want, but close. And then this is yeah, L delay. Let me see it. Yeah, here is the L delay, and here is T. That's right. See everyone? Here's T. This. So let me zoom in and find L and T. So your L. Oops. Okay, your L is almost 0.08. Say, can you please write the number for me? Okay, 0.08, and your T is 1.49, say 1.88 minus 0.808. So good. So it's gonna be 1.448. So let me write it down here. MATLAB code. So your L. So your L is 1.08, and your T that we find from the graph was 0.488 minus L. That's right? Because remember, L is from here to here, so you have to subtract from L. Everybody clear? Yes? Okay. So now I want to design the PID controller. Your PID controller is, what is that? Okay, is your KP is 1.2 T over L, because I'm gonna go back to Simulink. So your KP gonna be 1.2 multiplied T over L divided by L. Your TI is 2L. Your TI is 2L. And your TD is half of L. Half of L. I don't want to plot it here because it's too much. I just want to calculate those. So if you do that, let me So you see that your KP is 2112, TI is this number, and your TD is this number. So I'm gonna go to any sim PD. Okay. But based on what we have here, because I'm going to do MATLAB in Simulink, I have to multiply this by this and multiply this for this. So your let me do that. Derivative coefficient finally going to be Kp multiply. Okay, thank you. Kp multiplied by Td multiplied by Td and integrator coefficient gonna be Kp divided by Ti divided by Ti. Clear, everybody? Yes? Okay, so KPTD and KP divided. Okay, let's go to the Simulink. Again, this is not exactly what I want, S-shaped, but it's better than nothing. Hopefully it works. Okay. So we have PID here, so we're gonna do that here. Oh, let me run the code because I have to get the numbers. So you see that, okay, your KP was 2112. See that it's 21 KP, 2112. Your I controller. Oh. I controller was 132. 132. And your D was how much? This number. And this is derivative. Apply. Hopefully I didn't make any mistake numerically. And what was our system? Our system was okay, guys. Oh, I have a question from you. Our system is third order system, as we did here. What was the coefficients that we got for our system? The coefficient was this. Coefficient was this. Let me put clear all. Okay. The coefficient was this. Coefficient was this 1, 21, 100, 20, 100. I'm gonna copy from here and put it back here. Here we go. Guys, is this right? If I put this here? I want that you give me the answer. It's correct or incorrect? No. So those that we got was the result of this. That's right. What is this name for me? Open loop or closed loop? So you have to find G. Means you have to, whatever it is, -1. That's right. Yes. So your open loop closed transfer is gonna be 99. See what I'm saying? Because that 100 at the end of the day came from here. 100, 100, 100, well, why? See what I'm saying? So this is open loop transfer function here. Be careful. See what I'm saying? Everybody? Okay. Okay. Hopefully it works. Again, I'm saying because this is not exactly the S-shaped, and if we didn't do any mistake, hopefully, I'm gonna say final value 1. Step function. And so it's gonna be 10. Let me first try it. I have to double check everything, but hopefully it works. Here we go, bingo. Worked. It gave you an underdamped system and stable. Okay, so let me increase that time to 15. Here we go. So do you see? But again, this is the case that your system in MATLAB that we modeled is S-shaped function. This is not exactly S-shaped, but it works because it has the inflection point here. Gives you L and T, and we code in MATLAB. But just I'm going to share with you, because let me copy and paste in a new one. And I'm going to say here, save as PID Ziegler-Nichols. Okay. And if you run it here again, 15, because I wanna. Oh, guys, by the way, let me do this because I'm gonna make it complete. Oh, no. Also, you can plot in the simulink, you know, from what? The control input to the plant. This is control input. I'm writing here. U. This is U. This is error signal. This is U. And now, if I run it, see that the PID controller sends this command to the plant. Okay, starting from here. Don't. This is not starting from here. See here. Here, coming down, upping down. See. Okay. Let me make it larger. Here we go. This is like that. Coming to the minus to me, and then going up, and this is U. And obviously error signal goes to, tell me, goes to 0. So now you're expert of Ziegler and Nichols, which is very limited case, but works. Okay, everybody? Clear? Any question? Oh, here? Okay, let me run it. Oh, here we go. Okay, just let me do it again. Insert, go to insert. Okay, you see this? insert line, and then I plotted the line like this, and at the end, do you see this cursor? It shows that you can extend the line. Then I'm gonna put like inflection point like this. Then if you click one time on the line, by left and right arrow, you can change it from your keyboard. Do you see this? Like this. But I wanna put it on the inflection point, so I'm gonna I'm gonna move it down a little by the down arrow, and I say, okay, here is almost inflection point of that. Then this is gonna be your L, and this is gonna be until here, your T. Just zoom in, find those numbers. There are a lot of things in MATLAB that you have to do. That's why I expose you a lot in MATLAB, because I do believe if your GPA is cum to the power of n and you are not expert after MATLAB, maybe you are, I don't know, commuter between SDSU and home, but you are not mechanical engineer. Okay? You have to be expert after MATLAB these days, or Python. One language, okay? Even you can put the rectangle here, see? Here we go. Insert, whatever you do. Ellipsoid, arrow. You can put the arrow and put the text here that this is the tangent line. Whatever. Okay? So from where you can design your PID control. So almost we are at the end. I want to tell you, except that I'm going to hint about the root locus the next class. Yeah. When you look at the super heavy shuttle that Elon Musk sends to the skies, it's not magic, it's just the control science. They derive is pre-standard equation of the motion of the shuttle, which is completely nonlinear. Then they design controller. Okay, and you see that at the bottom of the shuttle that the engine sends out thrust forces. That's right. Those are not magic. These are based on those are this U. Look at here. Those are these U's. This here. U. Those thrusts are U going to the shuttle. That's it. Obviously, that is much complicated than you think. That's why it takes, I don't know, for the engineers of the Tesla, it takes 3 years that they drive the equations and then design nonlinear controllers. But you can say, okay, you know what? I'm going to linearize the equation and implement PID. Okay? Understand everyone? Okay. So let me stop this.